Hello, everyone. So, my name is Alexandru Dime. I'm a PhD student in SISSA in Trieste. And today I'll have the pleasure to talk to you briefly about a work of mine, a recent work of mine on neutron star simulations in screen modified gravity. So, to introduce the topic, allow me to start from the latter. Screen modified gravity is a class of theories, typically scalar tensor theories, that manage to do two things, precisely two things at a time. On large cosmological scales, the introduction of the additional scalar field with respect to simple GR allows to account dynamically for some cosmologically interesting effects, such as perhaps self-acceleration, which has applications in inflation models for dark energy physics. It can also give, for specific models, dark matter effects and whatever other cosmological effect you might be interested in. On the other hand, however, typically introducing these kind of modifications of gravity at large scales is hard to achieve without introducing also some effects that deviate from GR on small scales. Typically, we're talking about astrophysical scales. So here is where screening mechanisms enter the game. These are built-in features of screen-modified gravity theories that naturally allow the theory to suppress deviations from general relativity, for instance, on solar system scales, allowing the theories to pass automatically all solar system tests and to respect all our bounds that we are able to put on deviations from GR from essentially observations in the weak field regime. What about the strong field regime, however? Well, typically, because of the complexity of the task, screen-modified gravity theories haven't been studied extensively in the strong field regime. We are just recently, meaning in the recent decades, managed to model extensively general relativity in the strong field regime, and we are still exploring it. So doing the same thing in a more complicated framework is, of course, even more challenging. However, it's here in the strong field regime that this screen modified gravity may allow to put some constraints and essentially test the feasibility of screening mechanisms. For the rest of the talk, I will focus on neutron stars coupled to one of these scalar fields, which has a built-in mechanism called chameleon screening. In a few words, the chameleon screening mechanisms works by endowing the scalar field with a dynamical mass, which becomes very, very large, where the environmental density is large, in such a way that the large inertia of the chameleon field will suppress its dynamics, and essentially the scalar field will disappear in the background. So when considering neutron stars coupled to a chameleon scalar field, there are essentially three scenarios. The first one is the ideal one for the theory, where the screening mechanism is completely effective. Namely, the chameleon field will lie flat inside of the star because of the large mass, and will reactivate only in a very thin shell, essentially placed at the surface of the star. This is the so-called thin shells regime, where the theory leaves almost no observable sign of the presence of the chameleon in the phenomenology of neutron stars. The second case instead is the case of an unscreened neutron star. When the parameters of the theory are the incorrect ones, let's say, the chameleon field is not able to hide in the very dense regions of the neutron star, and essentially a fifth force is propagated even inside the star, modifying essentially the strength of the gravitational attraction. This could have very strong effects on the dynamics and structure of neutron stars. So this is the case in which essentially the theory, the chameleon model is ruled out, or is highly incompatible with the data, with the observations, for instance. The third case is a more subtle case, which hasn't been explored until recent years. It's what we call descreening, namely highly relativistic matter inside the neutron stars, inside certain neutron stars, can give an effect on the chameleon screening in such a way that the screening mechanism is broken by pressure effects. So these certain neutron stars with very dense cores can develop so-called pressure-dominated cores, where the pressure effect essentially gives the chameleon field a kick and reactivates it inside of the star. This is the case that is more complicated to study with analytical techniques. So what we did is to tackle the problem with numerical simulations. So in a few words, we constructed initial data for static chameleon neutron stars by using a TOV solver, essentially. We employed for our first step a simple polytropic equation of state prescription. And once we produced this initial data, we fed them to a 1+1 code that conducted the time evolution of these stars in a spherical symmetry. Here are the characteristics, properties of this code, but since the time is not so much, I will skip right away to our results. So our preliminary results regarding these descreened chameleon neutron stars were showing large deviations from general relativity for various realizations of the chameleon model, both in the structure, as you can see from the modified mass-radius relation here, in the spectrum of characteristic oscillations, where we saw both modified frequencies for the pressure-led modes and also the appearance of a new family of scalar-led modes due to the oscillations of the chameleon field. The third and probably the strongest deviation from GR, however, that we observed is a large emission of monopolar radiation during the spherical collapse of these neutron stars to a black hole. This large emission, it was so large that essentially we estimated that even in our local group, a chameleon neutron star collapsing will be very clearly and loudly observable from our detectors, current and future detectors. However, these preliminary results were obtained for a choice of the characteristic parameter of the chameleon theory, which is this chameleon energy scale lambda, which was very high, of order giga electron volt. This is not a viable parameter, it's ruled out already by other constraints. And however, going down to viable values of this lambda, which is around the dark energy scale, so milli electron volt, is essentially technically impossible for our code for the moment because of the large separation of scales inside and outside of the star. So what we did is resorted to an extrapolation, and we, to conclude very briefly, observed that there is no all the deviations from GR are essentially suppressed in the limit for lambda going to the milli electron volt scale. So with this, I would like to thank you for your attention. And if you have any questions, feel free also to write me at this address. Thank you.